Yes, HI is 1887.375.
Okay, so we got the Nusselt number for the tube side 215.44 and for the shell side 240, and
Yes.
HI is 188 point.
1887.3757.
Fine. So it's very close to this value, right?
Yes.
Oh, good. And for the, then you can convert it into tube side. You can convert it into tube side. Yeah. There is a formula given, right?
Yes. Multiply it by the inner diameter of the tube divided by outer diameter
Outer
of the
diameter.
tube.
Exactly.
Doctor,
yeah,
it will be for 1403.179.
Yeah, good. For the tube side, yes. And then for the shell side.
For the shell side. One 546.05.
Okay. So this is, yeah, correct. Correct. Yeah. Yeah. Good. Good. Okay. So then we can calculate the overall heat transfer coefficient, U naught. So when we calculating the U naught, we are not taking into account the falling resistance. When we calculating U, the next step, then we are taking into account the falling resistance. So you can do these two in one step or separately, doesn't matter. So overall heat transfer coefficient. Anyone got it? Overall heat transfer coefficient and overall heat transfer coefficient for while taking into account falling resistance, falling factor.
Yes, doctor.
Yeah.
I found without falling factors.
Yeah.
735.62.
Yeah. So it's same like my answer. Okay.
Yeah. It's
okay. Good.
735.617.
Good. Good. And then the falling. Then taking into account falling factors. So what formula you are going to use for that? 1 over U equals to 1 over U naught plus RDI plus RD naught. One over U equals to 1 over U naught. On page 470. On page 470.
Yes.
Yeah. On page 470.
What is RDI? What is RD naught?
Yeah, it's given on the Excel on my on the screen. I took it from the table. It is on my screen.
Oh, okay, that's after. Okay. RDI.
The value of the RDI will be 0.002.
Yes, it's given like 0.0002, 000, 0.000
For both of them.
for both of them, same.
Doctor, after falling, I get
Yes,
heat
Hadi.
transfer coefficient to be 0.0356.
What?
I get something less than 1
For what?
after taking into account the falling factors.
No, use the formula on page 470.
Yes, I used. RDI is 28.1.
0.0002 RDI.
There is RDO and RDI, right?
Yeah, the same.
They
value.
both are same actually.
Both are same.
Yeah, there is a slight difference, but both are same. Almost same.
Okay, I go for 568.37.
Yeah, that is.
Okay,
Yeah, that is what we got.
I see.
Okay, so we got the overall heat transfer coefficient. Now we calculating the number of transfer units n. Number of transfer units n. So the formula is given on number of transfer units is on page
476.
Yes, 476, page 476, number of transfer units. So find out that how much.
What is area?
Area is A naught. That is the heat transfer area. A naught.
Okay. Okay.
Doctor, I found 0.14056.
First, we have to find which one is minimum, right?
Yeah, which one is minimum? So minimum you can directly
Yes.
see from here because you have to calculate R, right? R you calculated is cold over warm, right? So cold is
Yes.
minimum.
Yes.
Cold over warm, and which is less than 1, so that means cold is minimum.
N equal 0.1405.
Same for me.
Cold is acetone, right?
Cold is
Yes.
acetone, yes, in the shell.
It is 0.1405.
0.1405, yeah, 0.141 I have written. Yeah, that is fine. Good. Okay, now we need to calculate E. That is on page 476. E.
E 476.
E we need to calculate.
This is very long formula.
Yeah, it's long formula. So other way is that you can use the chart. And the chart is
Okay,
given
which
on,
chart?
yeah, the chart is given on next page, 477. Right? If you know the value of C,
Yes.
if you know the value of N, you can get the value of E, either by formula or by chart.
Okay. See, what is C is
Okay, again,
clear
what
or
is
not
C?
clear?
Yeah, yeah, yeah. What
Minimum
is C?
over maximum.
Yes, C is minimum over maximum.
Okay, so
Minimum over maximum.
minimum or maximum. So 20 times.
So we need to calculate
So it
C.
is
Yes.
0.02.
C.
C is 0.94.
Yeah, 94, same like R. It should be
Yes.
same like R. Yeah.
It's same.
Okay, effective. Okay. 0.14. So
It should be same like R, right? So once you know the
Yes.
C and once you know the N, then you go to the chart and find out the effectiveness. So go to the chart.
0.55.
Pardon?
No, not
What is Sultan? What are you saying?
It will be small. Yeah.
Yeah, it
No,
is
not
very
small.
small. Yes, it is small. Check it from the chart. How much is it?
no. It was 0. Effectiveness is 0.55, right?
No, from the chart you have to see corresponding to N and corresponding to your C. So the chart that I'm
I
showing
saw.
to you from this chart.
I saw from chart.
Yeah, how much is it, Hadi?
0.55.
0.55. How much is Sultan?
0.1.
Yeah, it's 0.1 around actually.
Yes.
What? How?
From the chart.
Yes, from chart, but
Okay, what is the value for the C? The value for C is 0.9 something, right? It's close to
Yes.
0.1.
yes.
So this is the
Yes.
line. This is the line we need to follow, right?
Yes.
Yes.
This is the line we need to follow. And how much is the number of transfer units?
0.1.
Yes,
0.14.
it's small.
Yeah, 0.
So it's 0.002.
1.4 is less than the first one.
Somewhere here, huh?
Yes.
There is 0.2. at
This
the
is
line.
0.2, yes. And what is your number of transfer units?
0.1.
0.1.
0.1, so it's half of this.
Yes, approximately.
0.04 is effective.
1.14. So it's like 3/4 away.
Okay, 3/4, right, exactly, 3/4. So 3/4 somewhere here.
Yeah.
Yeah, so it's some 0.1, less than 0.1 actually. Oh, somewhere 0.1,
It is more
Yes.
than 0.1.
more than 0.1. 3/4, okay, 3/4, exactly. Then it is little here,
Yes.
little here, yeah. So 3/4 somewhere here, yeah. It's not moving properly. Somewhere here, 3/4.
Yes, exactly.
Yeah, more than one, exactly. So it is about what I got it 0.17. It is just what I took from the chart of formula. I use the formula basically. You see in my
Okay.
expression, I use the formula.
Safe. More safe.
Yeah, so it is. So first I calculated the numerator part and then I calculated the denominator part and then I calculated E. So it is 0.17. Now you got the E, then you can get the final temperatures. It's direct substitution, right?
Yes.
Final
Yes.
temperature. So, but final temperature, you have two formula depending upon the which one is less. Cold fluid capacity is less or warm fluid capacity is less. In our case, cold fluid is less. So we will use the equation 9.22, page 475. Page 475, 9.22. So first we will calculate small t2. On page 476, the end equations at the end, t2, small t2. So first we will calculate small t2, and then we will calculate capital T2.
You said, Doctor, figure 9.22.
Yes, equation 9.22, and the same equation given on the next page, 476 page, it is given towards the end. Small t2
Small
equals
T2
to
will be
T1 plus E.
25.3.
Yeah, 20.
25.3.
25.3, okay. And capital T2?
I don't see equation.
Equations, you don't see. Okay.
Oh, yeah, there. Okay, 8.
Can you see
T2
my
minus
slide?
T1.
Can you see my slide? These are the equations.
Oh, okay.
These are the equations. First one.
Okay. So, what is the difference between this A and that E?
You mean E?
A in equation 9.27 and
Yeah.
A in
Yeah,
equation.
depending upon which capacity is smaller. Warm fluid capacity is smaller or cold fluid capacity is smaller.
Okay.
So
Dr. T2 capital is 81.
capital is 81.2.
124.
Okay, good. So these are the
Doctor.
temperatures. Yes.
112, doctor.
No, did you use 30 as T2?
Yes.
T2 small.
Yes.
I think you have to use the one we got in the previous one, 25.3.
25.
Later we
Yes.
use
I
for
found
the
84.
No. T2 we will use the 25 because this T2
20.
this T2 is desired, which we have not got. So we have to
Okay,
this
yes.
T2. This T2.
Okay.
Yeah. So using this T2, how much is 81? This capital T2?
85.5.
85.56.
85.6.
56.
Okay, good.
5, 6.
Good. So anyway, so this is this meeting our requirement or not?
Uh,
Is this meeting our requirement?
No, we need 30. I think.
No, because we need to heat up to the 30 degrees Celsius. It's not meeting. So we need to do another iteration. So we have different options. Either you can increase the length of the heat exchanger, or you can increase the number of passes, or you increase the number of baffles. These are the smaller options. And or you can choose the larger shell size in the beginning. We choose 336 millimeter shell size. So you can choose the larger shell size and repeat the procedure and check whether you are meeting your requirements or not. So this is the entire procedure for the shell and tube heat exchanger. And then the pressure drop calculation are left. So the pressure drop calculation is same that we did several times in pump and piping network systems, right? So that is not a problem for you. You can do that. You can substitute the values in the formula and find out, okay? So because here we are not meeting the requirements, so what we need to do, we need to basically repeat the iteration. And while we repeating the iterations, we have several options. Either we can go for larger shell diameter, or we can go for larger length. We choose the 2 meter length, we can go for 4 meter length also. Yes, now tell me.
but here in the question, he said that the standard length of the copper tubes available are 2. So
Yeah,
can
this
we
is
change it?
standard length. Yeah, this is standard length. So you can choose another 2 also. Like 2 meter tubes are available, you can weld them,
okay.
and then it can make 4. So the next step will be the 4 meter length.
Okay.
Next step
So
will be the
use
4
2.
meter length. Yeah, yeah. This is what exactly I did. I
Okay.
did it. No, I changed the shell diameter also. I did 2 changes. If you see my second iteration, I changed the shell diameter, and I changed the length also.
Number of passes.
4.
Yeah. And yeah, several things I changed. Number of passes also I kept it 4. And length also I kept it 4.88. So it depends that which parameter you want to change, but better to change one parameter at a time. And the related parameter will automatically change. Like for example, if you're changing the length, then obviously the number of baffles will be changed, because baffles are placed along the length, right? So the number of
Yes.
baffles will be changed. So you can change one parameter. So when you see my recorded tutorial, in that there is a table, and they change it systematically. So I think it will be clear with that. Okay.
So I calculate using the
Sorry?
EU found in the second iteration.
Sorry,
The EU
what is-
found the second iteration. Yeah,
Uh-huh.
0.15.
You did the second iteration.
Yeah, but it found that T2 small is 56.
Okay, fine. So that is good.
So
that
what
is
we
good.
do?
That is good.
It's more than what's required.
No, it's more than what is required. What is required is 30,
Yes.
from 10 to 30.
Yes. Now
And
it's 56.
You are getting 56. It's very high.
I found
Yes.
Okay, listen to me. The next iteration, you have 2 choice. We choose the shell diameter 336. You go one step higher for the shell diameter. Okay, this is your one choice. Either you choose, either you do this, or the second choice is that you choose the length 4 meter or 3 meter. You get
Okay.
it, my point?
Okay.
Yes.
Right? You have 2 options. Either you increase the length in steps, like 1 meter, 2 meter, 3 meter, 4 meter, or you choose the higher shell diameters in steps. So any one thing you can do. And in the book, what they suggested to do, that you can see this, like I'm showing you the slide. Can you see that? Can you see the screen?
Yes.
So
Yes.
here, like the first, they in the second iteration, they only change the length here from 2.44 to 3.66. Again, they change the length, but still not meeting the requirement. Then finally they change the shell diameter. You see this? Can you notice
Yes.
this? Can you notice this?
Yes.
So this is basically here, and then here they change the diameter, shell diameter. And then still not meeting, then further they change the shell diameter. So first they go for length, you increase the length, what is feasible or reasonable length, 2 meter, 3 meter or 4 meter, and then next step you go for higher shell diameter. So I think it is clear now, is it?
Yes.
Yes.
Okay. Any
Again,
question
doctor,
related to, yes, tell me, Hadi.
what is the meeting criteria again?
Meeting criteria is that
That-
your temperature should reach to 30, because we wanted to, as we see in our problem was that we want to heat the acetone from 10 degree to 30 degrees Celsius. But we reached
Yes.
25 until now. So we need to use higher capacity exchanger.
Yes.
So either you go for higher length or you go for higher diameter, shell diameter.
Okay.
Doctor,
Yes, Salim.
I have a question.
Yes.
Could you please take off the question from, I want to ask about the number of baffle.
Number of baffles.
Yes.
You want to see the calculation for number of baffles?
Yes.
Okay. For number of baffles, in our
I
case,
know that we got that the maximum and the minimum. Why you choose 5?
integer value, because it either you can minimum and maximum, that any number you can choose in this limit. Any number you
in
can choose 5.
between.
Yeah, you can choose 10, you can choose 20, no problem.
Okay.
In between. So in between any number you can choose. We can choose 10, not a problem.
Doctor, is it has a relation to the efficiency?
Yes, it
Of
has a
the
relation
heat
to the performance. It has a relation to the effectiveness. So if
So
you
if you change the buffer,
if you change the number of baffles, let's say 10, your performance will improve a little bit.
improved.
Yes, your performance will improve, right? So your heat transfer coefficient, you see, are changed. Your heat transfer coefficient will change, shell side heat transfer coefficient will change, and then the overall heat transfer coefficient will change, and then the number of transfer unit will change, and then the effectiveness will change. Because the effectiveness here, right? It's changed now.
Yes.
It is 0.18 now. And the T2, I have not calculated. I just put your value. Otherwise, T2 will also be changed.
Maybe it will be better.
It will be changed.
26.7.
Yeah, 26.7. So
Okay, if you put number of buffers is like 28.
let's say you put it 28 here, number of baffles 28. Okay. And then see. Then see, because how much is the effectiveness? Effectiveness now is 0.2.
28.59.
28.5. So yeah, so it is affecting.
Yes.
It is affecting, yeah. So this is another option. One option is with length, another option is with shell diameter, another option is with number of baffles, another option is with number of passes also. Number of passes also you can change, right? Another option is with the pitch. The pitch you can reduce, tube pitch. When you reduce the tube pitch, you can accommodate more number of tubes within the same diameter. So that will increase your performance. That will increase your area. Area will increase, then your number of transfer unit will increase. That will increase your effectiveness.
Okay, Doctor, if like the second trial, the temperature T2 exceed by too much, do we need to do a third?
Yeah, if exceed
Titration.
too much, then you have to change it. But if exceeding by 2 to 5 degrees Celsius, leave it. Because this much, because there is a performance variation of the heat exchanger. So up to 2 to 5 degrees Celsius, your design is okay. Exceeding, not less, of course. If you exceeding by 2 degree or 5 degrees Celsius, you are still safe.
Okay.
Okay. So
Okay.
we decided to have quiz on Thursday, right?
Yes.
On double pipe heat exchanger.
14.
Yeah, 14 is on Thursday. Today is 12. So if you have any further question, then you can raise when we have next meeting, right? Because you have not seen my recorded lecture. That is why you have so many questions now. So better to see the recorded lectures also. And I hope that it will be very much clear because I spent too much time on recording the lectures and you will get benefit out of that. Inshallah.
Inshallah.
So, okay, so we can close the meeting today, and then we will see you on Thursday in quiz, inshallah. But anyway, anytime you have any question, you can send me on WhatsApp.
One question, Doctor, please.
Yes, please. Tell me.
The equation on page 475,
On 475, okay.
the equation
Which
of
equation number?
and
Equation number?
9.22.
9.22, yeah. This is applicable when your cold fluid capacity is less than warm fluid capacity.
So we can use that instead of 9.27.
The same equation.
It's the
In
same.
9.27, you need to calculate effectiveness. When you have effectiveness, only then you can use this equation.
But that is also effectiveness, right?
No. You can calculate effectiveness when you have E2, but E2 you don't have. T2 you don't have.
Okay, I mean T is small 2 or T capital 2?
Small T2, small T2 you don't have. What is given in the question is given that this is you need to achieve. This is not what the heat exchanger is giving to you, right? You got my point?
But to yes.
So effectiveness.
Okay.
So effectiveness you can calculate using T2 only when the heat exchanger is giving you this value. But when the question is given, it is the value that you need to achieve. It is not that the heat exchanger is giving T2. You got my point?
Okay, so we only use this like at the end to check.
No, this we use to calculate T2. You have to first calculate effectiveness and then calculate T2. It is vice versa.
Okay.
It's vice versa. First you have to calculate E and then calculate small T2.
Okay.
Yeah.
Okay, thank you, Doctor.
Okay, welcome. Okay, any more question? Let's keep it for the next time. I think because I hope when you listen the lectures, then it will be many things will be clear. Inshallah.
Inshallah.
Okay, thank you very much. Thank you very much for attending the entire session. You spent too much time today with me. Thank you so much. Okay.
Thank you.
Okay.
Thank you.
All the best.